Hi everyone, I'm Luigi. I'm here today to talk about Leaf, a tool we developed during my master's degree in computer science here at UFMG. This project was recently selected among the top 10 master dissertations in computer science here in Brazil, so I thought this would be a good time to talk about Leaf. Leaf is a tool whose goal is to transform code to remove what we call as sidechannels. So to begin with, we need to understand what are these side channels. And a side channel is essentially not an output of a system that is usually unexpected. So suppose we have a system that takes X as input, does some computations and outputs Y. Y is the result we are expecting to observe. But in addition to Y, we could also observe the power consumption, access to cache, running time, and so on. And these secondary outputs are what we call as side channels. And they alone are not problematic, but the problem arises when the input X is sensitive and there's a correlation between X and one of the side channels. In this project, we focused in time-based side channels. So just to illustrate a very simple example, suppose we have an authentication system that takes a user's guess and compares this user's guess with the actual password, which is sensitive, and the function does this comparison by looking at each position, and if every element is equal, then we accept the user's input. But if we find one element that is wrong, then we immediately reject the user's guess. So for example, if the first element is already wrong, then we reject the user's input on the very first comparison. And this implies that the running time of this function, or more precisely, the trace of instructions executed, will be different, will vary depending on the password, which is a sensitive information. So there's a correlation between the password and the running time, which could be explored. So how to fix this sources of leakage? One way we could try, one approach we could try is to equalize the conditional branches that depend on sensitive information. And this was actually the first solution proposed back in 2000 by Johann Agat, but it does not necessarily ensure the same running times every path. This was demonstrated in this paper from Wu from 2018, in which they opened the paper describing an experiment that shows that this approach does not work, at least not as we wanted it to work. And then they propose another solution that is to linearize conditional branches, which is the solution that we adopted in this project. So just to illustrate how linearization would look like uh, using the same password comparison example, the idea here is that we would completely remove that conditional test that exists in the original function, and we would insert instructions to ensure that the semantics of the program is preserved. So the city cell instructions here, which stand for constant time selectors, you could think of them as ternary operators in C, but in a way that you guarantee that they are going to execute in constant time. Or in assembly, you also have conditional moves. These constant time selectors are the instructions we add to ensure that we are preserving the semantics of the program. That is, that the transformed code will do exactly the same thing as the original one in terms of results, side effects. Um, and then we would like this linearization to satisfy a few properties. And the main thing here is that when we started working on this project, it was an open problem to deal with general loops statically. Previous approach, most of the previous approaches do not handle loops correctly, or they require loops to be unrollable. That is, they only work with loops that we can determine the number of iterations in during compile time. And even recent works still do not handle loops. We have two examples here, one from 2000, uh, from 2022, and another for 2023. Uh, and both of them leave uh, loops as future work, as an extension of the project. And there is one tool from 2021 called Constantine that do handle loops correctly, but Constantine relies on dynamic analysis. The idea here is that there's a training phase in which you need to run the program with some inputs, and these inputs they need to uh, you have to come up with inputs that exercise all branches, at least all branches that must be linearized. And it is hard to come up with such inputs. It's not trivial. And I'm just pausing here to talk a little bit more about Constantine, the way it works. Uh, in the case of loops, what Constantine does is you first run the approach adopted by Constantine is that you first run your program in the training phase with some input, and you compute an initial guess on the number of iterations that the loop is going to perform, and then when you transform the code, you remove every loop exit, and you create a single exit that is going to depend on a number of iterations. So, for example, let me go back to the first example, the password comparison. Suppose that we trained this function with um, n equals 100 and the guess equals to the password, then we learn that the function executed, the loop executed 100 times, and we use this number 100 as our initial guess. And then when we're actually after transformation, when you're actually running the transformed code, suppose that we feed function with an input where n equals 1000, and the user's guess is correct until the position 500, let's say. And what happens here is that the loop execute 100 times, then while executing, you observe that it needs to execute more than the initial 100, the initial guess. So it keeps executing until it finds a position that is wrong. So it executes 500 times and it stops. And then you update the limit of the loop from 100 to 500. And suppose now that you call the function again with uh, still with n equal to 1000, but now the user's input is correct up to the position 700. Then when the function executes, it is going to execute 500 times as expected. Then you observe that it has to execute more because it would execute more in the original version. So it keeps executing up to 700 and then it stops. And again, you update the limit of the loop. Any further call to this function in which the user's guess uh, is wrong and the position that it is wrong is less than 700, it is going to execute 700 times. But in this particular case, where we moved from 500 to 700, there was leakage. So you still have leakage. You are reducing leakage because every time you update the limit of the loop, you reduce the probability that the next call is going to force the loop to execute more than you guess it. But you still might have leakage. So Constantine's approach does not completely remove leakage. And what we want is a transformation that completely eliminates leakage statically. It has to work statically, not with a training phase. And we want transformation to be efficient or optimal in the sense that branches that do not depend secret must not be linearized. And also we want transformation to be memory safe. The transformation must not introduce invalid memory access, which is something that occurred in previous approaches like that one from 2018. And then we searched for a while. We tried to come up with a linearization algorithm, and we found this partial control flow graph linearization algorithm from 2018 from Moll and Hack, Simon Moll and Sebastian Hack. And this algorithm was developed in the context of vectorization. Their goal was to linearize what they call as divergent branches. And we noticed that we could adapt this algorithm to our context, the context of side channel resistance. So what they call as uniform branches for us are the public branches, the branches that do not depend on sensitive information, and what they call as divergent branches is what we call as secret dependent branches. So we adopted a small and hex control flow graph linearization algorithm and implemented a prototype, and we evaluated it against a few other tools, but we're focusing here on Constantine because it's the tool that also deals with loop. Uh, and we have a few analyses here. The first one is with respect to how much overhead transformation adds onto code. So we have here 9 benchmarks, and on average, they run 3.23 microseconds. And after our transformation, the average increases to 5.21. And for Constantine, it increases to 6.27, a little bit more. We also evaluated the increase on the number on a code size, and these two tools they were implemented on top of LLVM. So by code size here, we are considering the number of LLVM instructions. So again, on average, the original benchmarks they have around 330 instructions, and after our transformation, the average increases to 337. And for Constantine, it increases to 365. And lastly, we also evaluated the two tools in terms of security. We wanted to guarantee that the code transformed by our tool uh, does not contain any source of leakage. So we used two tools for that. The first one is CityGreen, which runs the code with some input and uh, informs you if some branch that depend on sensitive information was taken, which is the case of all original benchmarks except for cache 5, which we added here just to check that we're not introducing leakage to code that already was safe. And as expected, after our transformation, all benchmarks pass this test, but it's not the case for Constantine. And we noticed that the result for Constantine that they could be false positives. So we tried another tool, a different approach, and this time we used CFG grid, which uh, counts the number of instructions executed with some input, and after our transformation, all benchmarks pass this test, and for Constantine, almost all of them pass the test, except for two, which have already not passed the city green test. And the thing here is that this is this result is due to what we discussed, that Constantine needs a training phase, and you need to find inputs that are going to exercise every path in a program, or at least every path that must be linearized, and it's not trivial to come up with these inputs. So that's why we got these two fails here. So This project resulted in a few byproducts. The first one, we published two papers, one on 2021, which was a initial version of the linearization, which also did not deal with loops. It was published on CGO. And this year, we published another paper on topless, which is the actual partial control-flow linearization algorithm, the adaptation of Mo and Hex algorithm. And we have a prototype available on GitHub. We have an online interface, and also that first paper that was cited in this book called Low Level Software Security for Compiler Developers. Just to recap, the goal of this project was to come up with a transformation that eliminates time-based side channels efficiently and handling general loops, and transformation that is memory safe. And the solution that it came up with was to adapt Mo and Hack's partial linearization algorithm, which is uh, an optimal algorithm in the sense that only secret-dependent conditional branches are linearized, and our implementation is compatible with existing solutions. And the main thing here is that this partial control flow linearization algorithm was already in place. Our contribution here was to see that it was the key to deal with these side channels statically. That's it for today. Thanks.